how to solve for 1 plus 1. Now, 1 plus 1 is to be solved by breaking the individual components in half, which becomes 0.5 times 1 plus 0.5 times 1 plus 0.5 times 1 plus 0.5 times 1. Doing this again yields 0.25 times 1 plus 0.25 times 1, and the addition of 6 more of those terms. This can be, of course, done infinitely, but a shorthand way of writing this would be using the sigma notation, which uses the capital letter sigma from the Greek alphabet. This letter sigma actually has an origin story, believe it or not. So in the long ago, somewhere around the Levant, people wrote in a writing system that we now call the Proto-Sinaitic script. In that script, there existed a letter called shin that later evolved into the Phoenician letter shin before entering the Greek alphabet as the letter sigma. Now, you might be asking yourself, how is this history relevant to our discussion of what 1 plus 1 is? Anyways, so using the sigma notation, 0.25 times 1 added to itself 8 times can be represented with the Greek letter sigma, and with the number 8 above the sigma and a k equals 0 below it to indicate that it starts at index 0 with 0.25 times 1 as its terms. Now let's go back to what 0.5 times 1 added 4 times and compare it to 0.25 times 1 added 8 times, and you may notice a pattern would have emerged. See, when done 4 times, the coefficient multiplied to the number 1 is 0.5, which is equivalent to 2 over 4. And when done 8 times, the coefficient multiplied to 1 is 0.25, which is 2 over 8. Now, the pattern that emerges is how for every number n, the coefficient multiplied to 1 is 2 over n. Now, back to splitting these terms down infinitely. Doing this can be done using the limit notation shown as n approaches infinity. Now we have a formula here known as the Riemann summation formula. The terms are now n over 2 times 1, and a couple variables are in need of finding, which are shown in the general formula of the Riemann sum. This general formula appears in the form of limit as n approaches infinity, which encases sigma, the variable k beneath sigma, which starts at 0, and n above sigma, with the term as delta x, or the coefficient, multiplied by the function f of a plus delta x times k. Now that we have been introduced to this mysterious delta x, we must understand delta. Well, the letter delta actually has an origin story, believe it or not. So in the long ago, somewhere around the Levant, people wrote in a writing system. Well, anyways, back to our discussion of the general formula and what corresponds to what variable, it is obvious that delta x is equivalent to 2 over n, and we'll simply accept that. But how does f of x, a function, correspond to a number such as 1, you might ponder upon yourself? Well, f of x can be defined as f of x equals 1, and thus no matter what the value is inputted into f of x, it will always output 1. This means that in theory, no matter what the value of a is, f of x will always output 1, which means that a can be just about anything you feel like it being. So let's define a as 69 and say that in the parentheses within the function, we input 69 plus delta x, which is 2 over n times k, or in other words, 69 plus 2k over n. So now that we have defined a as 69, let us introduce you to the mysterious variable b, which has been with us this entire time. Welcome, variable b. Today we'll be solving for you, and to do that, we'll need the assistance of delta x. So delta x has a formula which is b minus a over n. Since we know that a is 69 and that b minus a is 2 since delta x is 2 over n, this means that b minus 69 is equal to 2, and since 69 plus 2 is equal to 71, this means that b is 71. Now that we have f of x defined alongside a and b, we can put this Riemann sum into a brand new fantastic form, a form that's kind of like a candy cane, a candy cane equation if you will, or what one might actually call an integral. Specifically, it is a definite integral from a to b with f of x, which is defined as 1 in the integrand, and ended off with our variable of integration, which is dx. Now, in order to solve this definite integral, we must utilize the power of the power rule, in which the derivative of x to the power of k is k times x to the power of k minus 1, in which k is a constant. Since an integral is the opposite of a derivative, or in other words, an antiderivative, we can define the integral of x to the power of k as 1 over k plus 1 times x to the power of k plus 1, in which k is a constant. Now, in our function, x is not present, but the number 1 is, so we can use the fact that since any number x to the 0th power is 1, that our 1 is actually an x to the 0th power this entire time right under our noses. So therefore, using the power rule where k plus 1 is 0 plus 1, which is 1, the antiderivative of x to the 0th power is 1 over 1 times x to the first power, or in other words, literally just an x. Now that we have integrated our function, we just need to subtract the antiderivative of f of x at x equals a from the antiderivative of f of x at x equals b. Or in other words, replace the x with the upper bound and subtract the same function but have x be replaced with a lower bound. Since our antiderivative is a simple x, we can simply just say 71 minus 69, which is 2. So at last, this means that our definite integral of 1 from 69 to 71 is 2, and thus, in conclusion, 1 plus 1 equals 2.
Sir, this is a Wendy's.